Oh my gosh, I almost forgot to remember. Oh my gosh, I almost forgot to tell you about the GitHub and what has happened recently. So, this is a friend of mine on I mentioned him before, and he is doing like a C128 and C64C version. So, I'll recommend you to try that or look at it. He doesn't have a PDF yet, so I suggest he does. He has ordered the board, but you must be warned that it hasn't been tested yet, so be very careful if you decide to try this on your own. Always make sure that it has been tested before, so you don't break your stuff. So, and same goes with my boards also. I have the GitHub, and I will link this link in below, and you can find the design files. There's the FIFO timer, and most importantly, you can see the discussion thread on Lemon64, the video playlist, so you are watching the videos anyway now, the Oshpark link, and a link to this GitHub though. So please check that out. There's a discussion there. I'm showing off my boards, and people are talking about it. Please feel free to contribute in any way you want. It's open source hardware, that means you can reuse all the schematics, the board layout, and all the design files. You can do anything, you can sell it. The thing you can't do is say that it's yours and you're going to make money on it and close down your source. Now enjoy the video. Thank you very much. Yes, I have soldered up this LED assembly, and I have made a little set of the pins and sockets. This is a prototype board. That reminds me I have to modify it before I send it. And I have programmed this microcontroller marked red is with the Disco Arch HR's version, and this is my version. And I'm giving him, I'm sending this to him because he's going to test it for me. So, and this is the board that needs modifying. So it's not the one I have ordered now, 10 of. The one I ordered 10 of has a better connector here, easier to connect the RGB LED. So anyway, he can program himself, he says, so that's fine. And then yeah, that's basically it. So I will have to modify this before I send this to him. Hello, hello. So this video I want to show you in real time. For once, I usually don't do videos in real time. I want to show you how to simulate the multi-kernel switch firmware in mikroC, and maybe also in mplab if you want to work in mplab. There's a good simulator there also. To do that you have to start a debugger. So, and the idea behind this is that maybe you don't have the development board that I have. So now you can see on the top that I've opened the multi-kernel project, and here's the code. And in the code I have added something called define debug, and what that does, you must remember this is C programming, so anything that is defined will be used, will be recognized further down the code. So if you go to debug, you will see that when I'm writing to EEPROM, this will only be done when we are not in debugging mode. So debugging is like simulation for us. So and here you have the read one. So the thing was that the debugger did crash. So And this is the latest microC version, so I have downloaded the demo version, so you can do it yourself. It's free, and it supports up to 2Ks of 2 kilowords of program memory. So if I build this one, click here, you will see that its project only uses 307 program words. So yeah, so we are far below within the limits. So this one is called Disco. So this because I'm simulating another project, but never mind. So let's show you the debugger. So what you do, you have to build, okay, and then you have to start the debugger. The watch window is where you can watch your variables and memory, so you can see what happens, and you can single step through your code here. So, and also if you start it, you can select a breakpoint, and I will get into that why you want your breakpoint to be on init outside the while loop. Also, we will use the run to cursor up here, because then we can put the cursor here, and every time we press the run to cursor, it will loop one time around loop here. So because this is a state machine, and you will see how it works when we simulate it. So the first thing we want to look at is when we're testing a system, we want to look at the outputs. So therefore we also want to stimulate it with the inputs. It sounds very perverted, but that's what it is. So we have something called JPIO bit 3, and you can search for it. It's a long list in here. Lots of stuff you can watch, but if you search, you can say GP 3 bit, and then click add. So, and if you press one of these on top here, you will just ruin the order that these appear. So don't do that. Just keep it like this. So now we have the input, and there should be another input. This is an input output actually. So we take this one also, the reset. So, and that's on bit 1. So here we have bit 1. Okay. So you have to remember that. I'm sorry about that. We can't get the real name here, so too bad there's no comment. And then we have the red LED. Those are outputs. So now we also want to see how the internals are working. So the first thing I think is that maybe we should know what the state are. So you can right click state in your code, and then you can take add to watch list, and there you go. It's in the watch list. So don't know exactly why the color is changing. Maybe because you are watching single bits here and not here. So yeah, maybe it has something to do with the data type. You can change the data type actually, like this. You can say you want to show binary, like this. The decimal is fine. So date state is a variable that is used to remember what state you're in. So we only have 2 states here. We have state 0 and state idle, and then state select. So, and the number of those states, it doesn't matter what those are, they just have to be different. And then other things, let's see, we are then having a button timer. We want to see how that works, so we add that button timer. And then we have my friend here has inserted something called ignore reset, so we can add that. So this is not my code, by the way. It's a part of it is my code. And yeah,
We have an old button also, we can look at that. Try not to add too much in here. So this is like a stopwatch, so you can follow how much time goes by. Yeah, maybe we should look at the kernel number also. And then, now the outputs. What are the outputs? The outputs are red LED, so that's GPIO bit 2. So, bit 2, let's add that. You just have to remember that is the red LED. And I will repeat that in when I demonstrate here. So, and then we have 4 and 5, those are address pins. Those are the one we want the microcontroller to set or assert, such that we can flip through the rooms, the room images or the pages of the room. So I think I got it right last time. So yes, here you can actually see it. We have a function called setKernel, and the kernel value that we put in there will fish out those 2 bits and set them into the GPIO port. So first we clear it and then we set the ports in question. So, and this means that it's shifted 4 bits to the left, and the reason for that is because address pins are on GP4 and 5, so we have to shift it 4 times to the left. Anyway, so let's run it then. Okay. The code has now stopped at init. So what I said, we are going to put the cursor here, and every time I press the go to cursor, it's supposed to get back to the cursor. But now it's not. So let's pause it. So I was mistaken. When I clicked here, it's outside the loop, so I have to click inside the loop, like this. Ta-da! So if you watch the... now this window popped up again. Maybe I shall just close it. So if you look down here, you see it's 1500 seconds. So let's stop it and then start it again. We have 0 microseconds. So let's do this again. Cursor's over here and step. Aha, 6 seconds. Right, so the initialization takes 6 seconds if this setup of my project is correct, though. I'm not sure. Click it again, we get about 100 milliseconds. So, and eventually you will get... Oh, it's my milliseconds, of course. So, and now we have seconds. 10 seconds. 11 seconds, and so on. So, now we can see that the GPIO 3 and 1 are both high. And what that means is that the input 3 and 1, those are restore and interreset. So when they are high, they are inactive, because they are active low because of this negated sign here. So that means that they are inactive. And when they are inactive, we shall not see anything change. So, oops, sorry. Let's get back. Sorry for the confusion. So what we can do now is to single step or run it to cursor through the loop. So let's see what happens. Okay, we set it to 0. Sorry about this, it's a bit confusing. We run it 1 time through the loop. What happens? The red LED is on, and we run. Aha! We have a button timer. So every time I go through the loop, now I'm clicking me through the loop, we'll see that the button timer is running. And how long? Well, I have a clause here that says larger than 15. So let's see what happens when you get to 15 and then 16. Aha! We are changing, our state machine is changing states, and the button timer now resets. And if I continue run it, you can see down here the time isn't running as much as it used to be. This is because there's no delay 100 milliseconds in my code anymore in the other state, which is it's in now, because now it's in this select state, and we have a smaller delay. This delay is used for debouncing the button. So okay, so what you remember from the videos, that when I use this restore button, you have to release it once, and then if you release it for a long enough time, you will then get a reset. And if you press it swiftly, you will scroll down, scroll through the ROMs. And now you can see the button timer is now increasing. We also have an old button. Just ignore that for now, because all button, this is used to remember that you had pressed it down, because when you press down the button it goes so fast, you think that's fast, but for the microcontroller it's an eternity, so it must remember when it the code loops a second time that the button was pressed, so it doesn't do the same over and over millions of times. So anyway, let's not talk about that. It's so confusing. So that button timer is running, and it goes to 30. But if I now press the restore button once again, check that out. GP4 and 5, you see those are address pins. So that's A13 and A12 and wait. Those are A13 and A14. So basically the lowest, least significant bit, the least significant bit of the address pins that we are controlling have now stepped up. So we are now on room 1. So we was on room 0, but now we are on room page 1. Fantastic. And we can now so put my thing there. Nothing happens, you see, as I'm looping through my code there to the eternal loop. I'm clicking, nothing happens. So you have to release it, right? Okay, so that the program can continue. And now, the button timer has started, and this one will go up to 30, I think. Yeah. So let's not go up to 30 yet, let's press the button again. And then let's see what happens. Ooh! Check that out! Now we are on room page 2. So let's do this step again. And okay, let's go through all of them. Boom! Now we are on page 3, the last page. And now let's release the button and let's see if it actually does a reset. So then we have to go to 30, and now I will single step the yeah. Well, you can see that the reset pin has been asserted. That means that it was 0 then 1 again. So okay, I'll do it again. Sorry for that. Okay, we must hold in the button to get into the change the state. Let's see. State is now 2, which means select state. We will release the button again. Ta-da! Timer starts. We press it again. We don't really have to do that to get a reset though. But now we have flipped one page. You can see now we are on 1-0. Maybe there's something wrong with the code there. Actually, I thought it was going to 0-0, but no. Let's see. Oh, yeah, okay, maybe it was. Okay, the timer goes. So let's have it go up to 30. there. And now let's single step. Let's see, because then we can see where this cursor goes. That's the interesting, you know. So let's step. We can step into, but then we get into the assembler code. So let's not do that. You see, the code just jumped all the way from state idle, and because state wasn't state idle, so you can also hover over it to see that state equals 2 there, and select state is defined as 2. So yeah, if I click this one now, yep, it's in the select state. Checks if all button is 0. It's not, so we'll jump over this one. Yep. It checks if both restore and interested is high, and all button is 1. Is it? No. So it checks if all button is 1, and then is one of them 0, restore negative, or interested. Oh, no, it wasn't. Here we have both high. Okay, let's see. It is. So it will increment the timer, do a delay. You see the timer is now 31, and else, it will jump over else. Okay, the button timer is now 31, so we will enter this this block of code, which now will change the state from state 2 to idle state, which is 0 though. So let's see what happens. There you go, state is now 0. See over here in the watch window. And my friend has added something called ignore reset, and ignore reset is 0, so it will do a reset. I'm not sure why it does it. I think it's to ignore reset at power on, because the computer will do a reset on power on, and this firmware that we are making here will not be waking up, sort of. It will not go into the select state when the computer pulls on the reset line, because the reset line is used for more. So okay, so button timer sets to 0, and we have now done a reset. We didn't see that actually happen, but okay, because we now stepped over this. So, but it did actually happen. So, and now enters idle states, as you can see. So let's try this again. Let's try see what happens inside the reset then. So first we must make it change state. So we let the button timer run out, and then we are in state 2, and we release the button. This, and if you go to 30 now, like this, and we step, timer, ignore reset. There, if we now step into, we can now get into this interested. Look, now we're in interested. We didn't see that before because we stepped over it. So okay, so let's see what happens. Okay, it sets the output to low, and that won't actually make the output low, because we must also activate the driver on that output. So that's bit 1 of the 3 states. So 3 states means that the output is not driven. Because this is a open collector, that means that there are many drivers on that, so so you must switch off the driver in your PIC controller. So let's continue. Okay, the LED flashes a little bit, just to show that it's doing something. And then again, delay, and then we turn off the driver again to release the interset. So, and then we, okay, this is something he has done now, so, okay, I don't think you need that. So, but yeah, maybe that's something. I never seen that, but maybe it's something. So I'm not going to comment it. So right. So now it gets out, and we are back here again. So this is how you can simulate. My friend has in my version, the restore button and the reset end button works in the same way, because I want that 1 second delay to wake up the select state. So to get into the select state, in case there are cartridges that issues resets and such. So I don't know, there's so much hardware you can get. So, but what he has done is that he just ignores the reset on power on, because the computer itself issues a reset, so this PIC can actually pick up that. So he has a delay on startup, so he doesn't actually pick that up. So so the idea here in his code is that he wants the state to change momentarily when you click. There's no button timer at the first click, so let's try that. You see, I clicked only once. I just looped through the while loop once, or the internal while loop, and we changed state at once. So, and then you can see that this is actually working, and then you have the button timer like before, such that you can now you can continue clicking on it. So maybe it's a little bit faster though, because you don't have to press 1 second to get into the select state. So there you go, change the state. We can loop it 2 times, and then timer goes out after 30, I think. Let's see what happens. Yes, the state goes back, and the butter timer goes back, and the reset has been updated, such that you get a reset. Right, so that works. So now just ask me questions if you want. Maybe I should show you mplab. I have recently installed it. I'm not a fluent at all in mplab. I know Gadget UK uses it, I think. So this is X IDE though. I can show you how to simulate there. You can't use my code in there though. So I wrote my first program, and basically it's very it's not really a program. It's just me testing out this concept of banking, because some chips when I'm using the C code, I don't think about banking at all. I just say, okay, I want and when I flip the internal registers like GPIO and 3-state IO, I just do that. I just call this. I don't really think about banking. So, but if you do a view and listing, and you can see what actually happens when you do that. It changes the status register bit number 5. And what's bit number 5? That's the bank. So it clears it over here before it accesses the GPIO. And you can also see there, if you see OCX0005, if you look in the datasheet, you will see that GPIO is in the memory map at address 5. But the 3-state IO is also in address 5, but it's in page 2, which is 80. In offset 80, plus 80. So, in hex. So get to that 3-state IO, you have to set the status register. So that's what I'm doing in this mplab, because if I don't do it, you can see what happens. What's the error? Illegal character. Okay. Sorry, I don't mean to sound pompous or anything. Well, I do when I talk to software. I'm always pompous. So let's build for debugging. So basically what this program does, it clears the 3-state I/O. That means that all 3-state bits are 0, and in effect you get all the drivers on all the GPIO to turn on, so you can drive the output, because you can have them as input also, you know. So then you have to set the input bits to high in the 3-state I/O. So then you do a debug, and then debug project, and then something is supposed to happen. Simulator, okay, it's running. It's running, yes, it's not supposed to run. So we break it. Okay, so what we can do, we can insert a breakpoint, and now this breakpoint is broken. It's a broken breakpoint. That's the funniest thing I ever saw. Okay, so let's break it here then. Or can I break it here? I don't know. It's broken. Let's do a no operation. Actually, that's the second operator I ever used in this assembler. So let's break on noop. Wait, let's stop the and let's clean it and build it. Let's see how it goes. So why I'm doing this? Because I want to stop the debugger before it continues to 3-state I/O. So yep. So let's run it. Build project. Debug run first. Supposed to stop. Okay, now it's stopped. Okay, let's right click 3-state I/O. New watch. Okay. There you go. It's in the variables tab. As you see, I don't know how to use this, so I will remove this one. Yep, let's see what's going on. Now, the thing is here that it clears the file 3-state I/O. So let's see if it actually does that. Then we can step over, okay. Now it's at clear F 3-state I/O. Let's click it. And nothing happened actually. So let's do the clear GPIO. Nothing happened. Because it's already 0. But why isn't 3-state I/O 0? Why are these all ones? Aha! Because when you run the clear F operator on a register which is not in the same bank, you are clearing the other one. So what we need to do then is to change the bank first. So this is just an example, so I won't bother you so much with this. So let's do a clean build. I don't think you do need to do clean builds actually, but okay. It's finished, and let's run it. Run the debugger. Breaks at nope. Let's click the variables tab. We have 3F on the 3-state I/O. We want it to go down to 0, but I don't think it will do that because 3-state I/O will never be able to go to 0 because it's an input only pin. I've talked about that before. It's really annoying, but okay. Let's see. Okay, status ARPA null is set. That means it's supposed to be 1. Let's see. Aha, something happens here. Status bit RP is now 1. That's nice. And now the 3-state I/O is supposed to be cleared. Let's see. Ta-da! Something happened. But it didn't before. And you can see, as expected, this bit will never be 0. So even if you write a 0 there, it won't be 0. It's just how some registers work. So and now we clear the RP0. Let's see. Yes, RP0 is now 0. And then let's run the last line, which is supposed to clear the GPIO, which is already cleared also. Yeah. And this code loops goes to nothing actually. If you go here to project properties and then when you look at the configuration, the debugger is now running in simulation, so we are not actually testing hardware. We're just basically we are just looking at variables and the memory position. But what you can do if you have a hardware like Pickit and ICD3, you can actually test in real time what the state of the registers inside of the chip is at any given time. So that's really great. So yeah, I think I'll leave it at that. Thank you very much for watching.